Thank you for being here today. We are starting this amazing new webinar series of the National Wildlife Federation that we are calling Building Climate Resilience for Wildlife and Youth. And our first presenter is Dr. Addriene Wootten. She's a research scientist with the South Central Climate Adaptation Science Center. Dr. Addriene Wootten specializes in evaluating the accuracy and uncertainty of downscaling and climate modeling, with emphasis on the use of climate projections outside of climate science, such as hydrology or water resources management. Additionally, she helps stakeholders with technological assistance and the appropriate use of climate projections for decision-making processes. She received her bachelor's degree in meteorology with a minor in statistics in 2008, her master's degree in atmospheric science in 2011, and her PhD as well in atmospheric science in 2016 from North Carolina State University. Welcome, and I really thank you for your time. And please, whenever you're ready to start your presentation, we are all ready.
Thank you very much. It's an honor. I forgot that I was the first one for your webinar series, so I appreciate the opportunity. Thank you so much for having me. I've been looking forward to this. Thank you also for the introduction. And as Rebecca said, I work with the South Central Climate Adaptation Science Center, and I figured in brief, just for those who are maybe unfamiliar with us, the South Central Climate Adaptation Science Center, or the South Central CASC, is a partnership between the USGS and a consortia of universities and tribal nations in the region. And we basically focus on natural resource issues and climate change adaptation for the South Central United States, which for us is Texas, Louisiana, Oklahoma, and New Mexico. We are one of 9 centers across the United States, all under the name of Climate Adaptation Science Centers. Of course, if you want to know more about that, please feel free to ask. So today what I'm going to talk about is the future changes in the climate of Texas and the potential impacts that there will be to spring phenology across the state of Texas. What I want to get into is, of course, just for those of you who might be a little familiar, bring up a little bit on what the climate projections themselves are and how they're constructed, but also then get into some basic changes that we expect to see based upon those climate projections, and then go into the final thing here, of course, and probably what most folks came for, is the impact that potentially will happen to spring phenology across the state of Texas. So without further ado, hang on. There we go. Weather versus climate. So when we're talking about weather, it's the state of the atmosphere with respect to hot and cold, wet and dry, calms or storms, clear or cloudy. It's really short-term related things, whereas climate is always that statistical collection of weather conditions at a place over many years. Often it's a 30-year period is what we use, or at least a 20-year period, but it's over a long term. And actually, Mark Twain's quote on the subject is actually pretty accurate for what the difference is. And climate is what you expect, and weather is what you get. Climate projections themselves have 2 different definitions according to the Intergovernmental Panel on Climate Change. In a general sense, they're any description of the future climate and the path that leads to it. It's not just what the future climate itself would look like, it's how do you get there. In a very specific sense, they are model-derived estimates of the future climate. Now, of course, one question we often get is, why do we even bother using these climate projections to begin with? Why do we want to know with future climate information? Why can't we just use past historical observations and what have you? Those do have their value, but you might think of it this way. If you're using just past historical observations of the climate, you might be essentially driving down the road while looking in your rear view mirror and not seeing what's going on ahead of you, assuming the future is going to be a lot like the past. But that can be pretty poor assumption in climate as it can be in driving, because that all works well if the road in front of you is pretty much straight, just like the road behind you. But if there's a curve coming up in the future, of course, there you, as my mother would say, you would fail to negotiate the curve if you're just looking in the rearview mirror and go crashing off a cliff. And in a similar fashion, if the climate is going to curve in a direction that hasn't been experienced in recent history, that becomes a concern then if you're just relying entirely on past observations. We do have a lot of projections actually of climate change, and this is an example from Oklahoma City, but you can run the same kind of example for everywhere in the world, really. And doing a lot of long-term planning and adaptation and looking at possible changes of spring phenology requires some of these long projections. So this is a projected change. So how much warmer will the high temperature be in Oklahoma City compared to what we know currently? And this one's in degrees Fahrenheit, but this is one example in here. But one of the things that kind of surprises a lot of folks at times is that we actually have very many, because this is the range of projections actually just for the Oklahoma City area for how the high temperature would change out to the year 2100. There's a lot of different reasons why we have those particular that particular range of projections here, and that's what I want to walk through just to give a little bit of background as to what we're talking about. The first reason for this is it has to do with the emissions scenarios and the temperature change itself. So these emission scenarios are basically what ifs. What would society do at large, if you will? Will there be more burning of fossil fuels and release of carbon into the atmosphere, or will there be less as you go out into the future? That's what's shown on the left-hand side here, actually, is a graphic representation of that what if with society at large. How will those emission scenarios go in the future? So that higher scenario is an RCP 8.5, and RCP stands for representative concentration pathway. But the main gist of this is that it's a scenario where there's a larger release of greenhouse gases into the atmosphere from human activity in one form or another. Whereas in the other two lower scenarios, there's lesser degree. What happens with these what if scenarios, if you will, of human action is the carbon emissions and the other emissions of gases like methane and nitrous oxides and what have you are provided to one of the other components of climate projections, the climate models, to then say, okay, if this is the human societal action that happens at large, not just locally, but at large in global and national levels, what would be the response of the climate globally? And that's what shows up on the right, actually, is the response of the climate as represented by the climate models in these particular what if scenarios, where you can see the higher scenario is a warmer future according to the projections going out to 2100. When we talk about the models that provide projections, these are global climate models, and they're all founded on fundamental laws of physics: conservation of mass, momentum, energy, all the rest that you may have learned in a physics class. The way they work is they're divided basically into a grid across the Earth, latitude, longitude, but also up into the atmosphere and down into the ocean. And at each of these locations, there's a complex set of equations that are calculated for every single timestamp that then gives us estimates of temperature, precipitation, air pressure, relative humidity, wind, sunlight, and on and on and on. There's actually a very long list of variables. Those equations involved actually encompass all of those particular physical processes you'd see in this particular graphic. The interaction between ice and ocean, for instance, cloud formation, all sorts of different particular features. The purpose of climate projections, the climate models, are not to provide exact detailed predictions of what's going to happen, but rather to give us a reasonable projection of a physical change, to tell us how what is typical now will change in the future. Not on this day 50 years from now there's going to be a thunderstorm. That's not the purpose of a global climate model in those kinds of sense, but to give us a real reasonable projection of physical change and a realistic representation. Like this is actually an example of output from a global climate model, in its representation of storms and frontal systems and hurricanes across the world. We look to see these kinds of representations, and that the physical climate that we know is actually there and realistically represented in a global model. And in this case, this is a very excellent example of that. The problem with the global climate models, and where we get to even more projections, is that to produce information for the entirety of the world, those boxes that are used for the global models have to be relatively large, in the order of 100 kilometers by 100 kilometers on a side, or 60 by 60 miles if you prefer. And that represents some interesting challenges when we're talking about phenology and ecosystems and the like, where things are impacted by climate change at very local levels. There's another process that we use called downscaling that helps to address that. It's a whole additional modeling process, and where I spend most of my time in research. The box on the graphic on the left-hand side here is temperature output from a global climate model. And the boxes here are 200 kilometers by 200 kilometers each. Now, you should expect to see a lot of decrease in change in temperature with elevation over very short distances, with the mountain ranges, with the Rockies and the Appalachians in particular. And you notice that's kind of not there, right? Because there's only one number per 200 kilometers. So some of the different valleys and mountain ranges aren't represented as well as we would like. And it's only that size because it's computationally very intense to run across the entire globe. But those features with the mountains don't go away in a future climate. So we add the process of downscaling to make sure those particular features are represented, and to increase the resolution, which is to say to decrease the size of each of those little grid boxes, and make that information much more useful for answering stakeholder questions about how the climate will change in their location, for impact assessments, and better represent a local climate. So that's what the right-hand graphic is. That's reduce the size of each of those grid boxes to 25 by 25 kilometers instead of 200 by 200 kilometers on the left-hand side. And now you can see all of those changes in the Rockies that you really couldn't before, alongside of seeing the Appalachians. So those are the kind of three main things that make climate projections what they are, and as complicated as they can be to work with. So what I'm going to be spending much of the rest of the talk talking about the actual projected changes that we see themselves from a data set that we have produced here at the South Central Climate and Adaptation Science Center, and we'll be updating here in the next year or so, from the Climate Projections Evaluation Project, or you might say CPREP, which actually encompasses a few different things here. And I won't read through all of this, but it's specifically designed and built for this region of the South Central United States to capture our unique climate, which has very transitions in Louisiana, and Texas is a good example of this actually, because it's very wet in East Texas compared to the much drier Western Texas. And it's of course much warmer along the southern border of Texas compared to the northern border of the state. And so this kind of complex and unique climate is what we try to capture with the downscaled climate projections that we've produced. In the set of projections we actually have 27 of them in total for each of those emission scenarios, those what ifs, and for each variable we produce. But to make it easy to look at and get a snapshot of what change would be, we'd often take a mean of those 27 together to see what the average change would be in the future. And that's most of what we're going to look at, though I will show you where there is also some variability and a little bit more uncertainty in some of the projections, areas where we have a little bit less confidence. So there's going to be a lot of these, so let me walk you through it first. Each of these maps represents the mean change from those 27 projections that I mentioned. This particular variable that you're looking at is for the annual average high temperature. So for your daily high temperature on a given day, how much warmer will it be in the future? We're talking end of century, so this is 2070 to 2099, over a very long time period. Of course, we can do a little bit in the middle, but I went with the end of the century for this one. And the left-hand side is the average change under that lower scenario here, which is less fossil fuels going into the atmosphere, more sustainable growth and development, those kinds of aspects. Where the higher scenario on the right-hand side is the right-hand side is the map of the mean projected change in the higher scenario. The legend here will always be on the bottom. And actually these two numbers in the top right of each one is the average over the entirety of the domain. So it's not just Texas, but it is the average change over the entire domain. And kind of the biggest thing to take from this is that you're just annual average high temperature here, and particularly under that high scenario on the right-hand side, by the end of this century, by 2100, is projected to increase by up to 5 degrees Celsius. Now, if you prefer in Fahrenheit, that is about 9 degrees Fahrenheit here in the state of Texas, with much warmer temperatures in the panhandle of Texas compared to along the Gulf Coast. There's a lower scenario is a lesser degree of change, which mirrors a lot of what you see just looking at the global temperatures also. Same kind of thing where the higher scenario is warmer. One of the things that's great though for us, since we're talking about phenology a little bit today, is you can also get into looking at, okay, what does it look like over different seasons? So this is just for the high scenario, but it's the same kind of thing. Each of these maps is the mean projected change, and it walks through from winter on the left to the fall on the right. And you can actually see the greatest increase in temperature, just in generally speaking, is during the summer, but even the winters would be getting a fair bit warmer here across the state of Texas, and particularly in Western Texas, which again has some you all may be already thinking about it, what kind of implications this would have for spring phenology across the region. One of our prime concerns, of course, not just for wildlife, but also for humans, is okay, how much hotter are some of these other things? How much hotter is it going to be? Then what does that have an effect on in terms of the extremes of temperature? What these two maps show is the projected change in the number of days per year on average, where the high temperature is greater than 100 degrees Fahrenheit. So I know a lot of people here may remember 2011 and 2012 and how hot and dry that was. That's the kind of things that we're looking at here. How much more likely would that kind of thing be in the future? You can see in the low scenario on the left-hand side, it does increase. There are more days with the temperature over 100 degrees in a typical year, but it's not anywhere near as much as what could be, particularly along the Big Bend area and into southern Texas, where it goes over 80 days more than what you have currently in terms of number of days where the temperature goes over 100 degrees. So it says a lot for well, it may say a lot. I will say this, I am not myself an expert in wildlife, so this would be a question to put to those of you watching. Is something like this happening? What would that mean for the wildlife in the area? Or do you have a sense of what would it mean? It may not, may do, may not, but you all would have a better sense of that than I would. So one of the nice things, though, that we can do with the downscale projections is start to look at different places across the state of Texas and get a sense of the confidence also. So basically, the way to interpret these bar graphs is the top of each bar, like this red bar here, or this blue bar here. That's the mean in the map that you saw, but it's the mean for that particular area. In that case, the one I was pointing at is El Paso, Texas. And the black bars in each of these are basically a 95% confidence interval based upon the 27 members and 27 projections that we have. And you can see these are relatively small bars, so we actually have a lot of confidence in these projected changes in across the region. This is Amarillo up here in the Panhandle, Dallas, El Paso, and Houston. Houston being the lowest change because it actually has some of its temperature change moderated by being right along the coast there. And but the rest of the region, anywhere from a little over a degree Celsius increase to close to 5 degrees Celsius increase in the annual high temperature. I know for some animals and plants, there's also, during the evening when things cool off, there's less stress and animals and plants can recover from that. So of course, the other question is, what about the low temperature? And one of the projected changes that we expect is also the low temperature will get warmer also. So your evening temperature won't provide as much relief as it could as it did in the past, as you get to the end of the century in 2070 to 2099. So again, Amarillo, Dallas, El Paso, and Houston, covering areas of Texas. I'm sorry, I didn't think to put San Antonio in here. I saw we had a bunch of folks joining us from San Antonio, but you can make some you can definitely make some guesses. And of course, if you're interested in having more information on San Antonio in particular, we're happy to work with you on that. That's one of the things that Cask and I myself do on a regular basis, is to help provide that information for folks who want to use it. Of course, the other graphic that we just looked at was the number of days the high temperature goes over 100. And again, the 95% confidence interval, the bounds on that are pretty small. So there's a lot of confidence in each of these for all of these locations. And Houston is nicely moderated, but it will be quite a number of days with the high temperature over 100 degrees in all of these regions. Now, as I said, there's a lot of confidence in temperature. There's a bit less confidence in changes with rainfall, and we'll get into a little bit of that in a second. But in general, what we expect to have happen is that, particularly under that high scenario, things are going to get drier. I heard somebody mentioning about hot, dry Odessa, Texas. Well, I'm not quite sure exactly where it is on the map, but it may be hotter and drier as you go into the end of the century, with 10% or more decrease in rainfall in certain areas of Texas, and closing in on 20% if you're going near El Paso. So it certainly represents an interesting challenge for a lot of the different species and ecosystems in Texas. And what is dry gets drier here under that particular high scenario. Again, we can also look at this seasonally too with precipitation, and it's often a good thing to look at, although in this case with precipitation in Texas by the different seasons, it generally just decreases for all the seasons. I know there's a lot of concerns about Big Bend National Park and a couple of the different ecosystems along there. And this is a good thing to see, for example, the increase in precipitation in the headwaters of the Rio Grande. But bear in mind, with the warming temperatures in the winter, that may not fall as snow, that may fall as rain. And that's kind of one thing we have to tease out working with temperature and precipitation. But in general, across the state of Texas, even in all the different seasons, even winter, the amount of precipitation available from that high scenario will decrease. One of the other ways to look at this is just in terms of number of days of rain. In a warmer atmosphere, because it takes longer to reach saturation, it takes more time to build up enough water vapor in the atmosphere to reach saturation and to start raining, which translates into fewer days with rain. And that's what we see with this higher scenario, is that just everywhere in Texas, fewer days with rain in the future in a typical year. At the same time, one of the things that can happen is that it takes longer to build up that amount of moisture in a warmer atmosphere. It can hold more moisture before it starts raining. But when it does start raining, that means there's more moisture available to rain out of the atmosphere. And so at the same time, particularly in eastern Texas, in the Houston area, and in the southern tip of Texas, the heaviest rainfall events start becoming much heavier. So think about flooding rain events in particular that could be hurtful to ecosystems and to different species across those particular areas of Texas. So like I said, there's a little bit more spread with the error bars for some of these things with precipitation, and that's part in trying to figure out, there's a little bit of uncertainty, for example, in exactly where the jet stream is going to be in different seasons, which provide some of the weather systems that bring precipitation into parts of Texas, alongside of things like the hurricane season and where hurricanes will end up and how much more or less intense they would be. But in general, the drying trend is observed here, even if the error bars are a little bit larger. And again, Houston seems to be the outlier for us along the Gulf Coast, with a little bit less of a decrease compared to other parts of the state of Texas. Similarly, the number of days with rain is actually pretty consistent all the way through here, with a decrease in the number of days of rain across the state of Texas. The other one that's a little bit odd is, again, the one-day rainfall, those extremes of rain, you can see it for sure in Houston with an increase in the intensity of those one-day rainfall events in the Houston area. In some places also, there will be a lesser degree of an increase, though, again, there's a little bit less confidence in some of those things for the reasons that I already mentioned. So with that, now we can finally get to the impact side of things, the spring phenology itself. The climate projections are always wonderful tools and visuals that we can work with. And they are, the climate itself being about typical weather and the frequency of extremes. And of course, the next question is, why does it even matter to see how the climate will change? Because you may be thinking about, okay, frequency of droughts and growing season and frequency of heavy rains and the high temperature. That means different things for growing of crops, for ecosystems, for the spring phenology itself. And it is because of things like the changes to ecosystems that may very well happen as the climate changes, that we get concerned about seeing, what does this mean for things like spring phenology? And so more studies like this tend to pop up. So this is an example from examples from Puerto Rico and changes in species richness in that particular, in the Puerto Rican uplands, for example, or even getting into warming winters, reducing the chill accumulation, having an effect on peach production, because it is not just ecosystems, it's also agriculture that is impacted by this. I saw a raised hand if somebody wants to jump in and ask a question.
Did you see a question coming?
I thought somebody raised a hand. I saw that, but
Okay.
but we can wait until the end. I'm happy to take all sorts of questions at the end. So one of the things that we can look at with the projections is related to all of this is the change in the length of the growing season. And as you'd expect, with warmer temperatures across much of the region, the growing season length in the state of Texas, and indeed across much of the South Central United States, is projected to get longer. And so earlier flowering times, earlier leafing times, and a lot of other important changes. I know, at least in the USGS, they've been thinking very much about what does the change in the climate mean for phenology with regards to bird migration stopover and tree phenology in the Central Flyway, which includes the state of Texas and the Central Flyway. So one of the things that we get into here is looking at first leaf and first bloom from a handy set of indices called the extended spring indices, created by Schwartz et al. And Alstead et al. It's been very well used, as I understand it, by the National Phenology Network. And one of the things that we've added here is a little bit on the late fall spring exposure, which is to say this is when a hard freeze occurs after the first bloom. It can be very damaging to plants that have already started blooming. And calculated in-house here using the same set of projections and the high and low temperatures that we have. So for an example, one of the species that I know USGS has been interested in is the whooping crane, which migrates along the Central Flyway. And a late fall spring is when a hard freeze, where the low temperature is less than 28 degrees Fahrenheit, occurs after the first bloom. But it's also very dependent on the first bloom date and timing and the intensity of those cold extremes in the future. So from the daily low temperature and the daily high temperature, we can say something about the number of days the low temperature is below 28 Fahrenheit, the accumulation of spring heat, the first leaf date, the first bloom date, and then finally the late fall spring itself and the likelihood of having a late fall spring. So based on the extended spring indices and the projections of high and low temperature that we have here in-house, we went ahead and calculated an estimate of of how the day of first leaf and the day of first bloom may change across the state of Texas and across the South Central region. So how you should interpret this is any negative values means the day of first leaf is going to happen earlier in the calendar year, going in here for these different regions. So as you can guess, with the warmer temperatures, the first leaf generally is projected to happen much earlier, 2 weeks or more on average in the high scenario. This is not to say for individual species, because the index we used is a very generalized index. It kind of gives an overall sense, but it doesn't speak to any specific species that might be of interest to someone. So that you have to do a little bit more calculation with, but in a general sense, we expect the day of first leaf to happen earlier in the year, and much earlier in the year in some places by the end of the century. The first bloom is similar, actually, and the first bloom becomes even a little bit earlier, on average, being about 3 weeks earlier on average across the region in the high scenario. So this is, again, interesting things. What does that mean in terms of the timing of ecosystems and what have you? Because for me, who is primarily a climate scientist, it's of interest to me for sure to hear from you all what these kinds of things might mean for the different ecosystems and species you're interested in Texas, in Texas wildlife. What is more curious of a thing to see is the risk of a late fall spring, a damaging freeze happening after the first bloom of the year, or hard freeze happening after the first bloom of the year. Much of Texas, that's a negative number in the high scenario, and under the low scenario barely changes at all. But under that high scenario, much of Texas is negative, meaning it becomes much less likely in the future. But the exception to this is actually in the panhandle of Texas, where there's a couple of places where it becomes actually more likely in the future to have a hard freeze happen after the first bloom of the year. And this is certainly interesting when you're talking about different species who may be relying on those blooming plants in their interactions and in the phenological processes that are there. So this is a tricky challenge to work with, is managing that. And the idea is, even though the first bloom moves earlier in the year, you're in a portion of Texas where you'd still see a significant number of hard freezes in there. So it actually does become more likely to see a hard freeze happen after the first bloom at the end of the century. Likewise, we can look at things like the growing season length in different areas of Texas here, and in this case, making it almost 2 months longer in some places like El Paso and Dallas, or a little over 40 days in Amarillo, and a shorter 30 days in Houston is a good way to look at it. Because these are so temperature based and we have a lot of confidence in how temperature is going to change, a lot of these error bars are actually much smaller than for precipitation itself. On the other hand, of course, first bloom much earlier in some places, and in particular Amarillo, there the first bloom is almost 25 days earlier under that higher scenario. In the top left here is what I am looking at, with Dallas and El Paso and Houston being much less of a change in the day of first bloom, still earlier, but by less than 2 weeks in this particular case. In some places, not even any change at all. But as I mentioned, the late fall spring and the likelihood of having that, so higher positive numbers being more likely, negative numbers being less likely to happen in the future. That's a little bit less confident in here because it does rely on changes in the cold extremes, which there's a little bit less confidence in some of that from a few things that we found with how the different downscaling techniques handle that. But that's a conversation I'm happy to have if you want to know more. But Amarillo more likely to have a late fall spring, that hard freeze happening after everything starts to bloom, and the like. Whereas elsewhere, it's a pretty much less likely to have that happen in the future, which is in a way a good thing, to have plants not be damaged by a freeze shortly after they start blooming. So in conclusion, we're having increasing temperatures in Texas are projected, and this will likely lead to more warm extremes and warmer winters. Generally a decrease in precipitation, fewer days with rain, but more heavy rain events are distinctly possible, particularly in eastern Texas, Houston area. And warmer temperatures can drive some pretty dramatic changes, or could drive some pretty dramatic changes. it's quite likely the first leaf and the first bloom will move even earlier in the year. And it's less likely, for the most part, that there will be a fall spring or a freeze happening after the first bloom of the year. And so with that, I think we did pretty good time-wise. So we can jump right into it because I can see messages popped up in the chat. So I'm happy to jump right into having some question and answer.
Yeah, there's a question in the chat if you would like to address that, and the rest of the questions, if you guys would like to drop them in the Q&A box, that would be great.
Okay. From Julie, I was wondering if you mentioned or included anything about photoperiod in the phenology models. I did not. I'm not familiar with photoperiod in here. The phenology calculations with this are primarily temperature based because the extended spring indices only require high and low temperature. Though there is a calculation for day length that is done in there also based on the latitude. But I don't have a thing not in those calculations is there something specific about photoperiod. I hope that answers the question. Okay, good. I've not heard it called photoperiod before, so that's why I was confused. I always referred to it as day length. Thank you for clarifying that.
Yes, so, okay. Thank you for that question, Joe. And if we have more questions, please make sure to drop them in the Q&A box. Yeah, I share with you guys a definition of phenology, just in case you are not like fully familiar with it, as well as some examples. And Dr. Wootten gave us some examples during her presentation as well. But I think one thing that we could do is reflect on the effects of climate change in wildlife, as she was saying, phenology, especially, and what will happen in each one of our cities here in Texas. That's really, really important. And if you have some examples, something that you have observed in your community, in your city, please feel free to share. One thing that I can share with you all is that a couple of years ago, we noticed, and actually this year as well, we had an experience with native milkweed blooming, the seasonality, and the migration of the monarch butterfly. Mm-hmm. So we had a late blooming of native milkweed in some areas in Texas. And that was extremely late for the monarchs that were coming back from their overwintering grounds in Mexico. And it was a bit concerning because especially here in Austin, we noticed that there was no milkweed available for monarchs. And we continued to see them passing by without any chances of them finding enough milkweed to lay their eggs. And fortunately, there were some nectar plants available for them, so they could refuel and continue their migration. And hopefully, they were able to find enough milkweed to lay their eggs. But that's a really good example of what could happen with climate change and the effects on phenology.
Definitely, that is a great example of what we're talking about, where the change in the climate has started to affect how early or late something will bloom or even start to leaf. So that's a great example.
Yeah, and Lynn is sharing another example in the chat. We noticed native milkweed blooming late. Thank you. Is climate change predicted to affect agriculture? Has it been studied? That's a question that she has.
Mm-hmm. It actually, there's been a lot of studies with agriculture, and there's a lot of concerns that there's going to be some effects to many different species of agriculture of crops. For example, colleagues of ours have been studying maple trees, which produce maple syrup in the Northeast US. And there has been an impact on them. They're having a hard time building up the sap that they would normally be drawing off to make maple syrup from those trees as the climate has gotten warmer. So it is definitely projected to have an effect on agriculture, and there's been a lot of studies ongoing as to how much of an effect and on which crops. Another good example is apples are generally grown in New York and in other northern areas. They tend to need a little bit more cold air. So the concern is, as the climate warms up, will you be able to continue to grow apples where they've been grown? Similar concerns actually for grapes in wineries. So that's a whole other concern. So yes, is the answer to that.
Okay, we have 3 more questions. One that was dropped on the Q&A box, and 2 more here in the chat. So
I don't know which one came in first, but
get to them. Let's see Betsy's question, which is in the Q&A, and then we'll address the other 2 ones. Where I live, I feel like 2022 is your 2070. A year ago, our ranch in Ector County received more than 15 inches of rain by July 29. That was our last day of precipitation. Since then, I have recorded 1.42 inches of precipitation in my
it's a CocoRa's gauge.
Yes, yeah, the CocoRa's rain gauge. Yeah, I'm familiar with other ones, but not that one. So thank you. That's a new one for me, Betsy. So that was a comment. And then Kristen, does the calculation for length of growing season take into account changes in temperature with respect to temperatures being too high?
Yes, it does take that into account.
That's great. And then Gary, is it true that rising Arctic temperatures and the breakdown of circumpolar winds will increasingly allow Arctic air to penetrate deeper into continent in the early spring, causing unseasonable freezing weather?
That is a possibility. That relates to the jet stream, because the jet stream is that manifestation of the temperature and pressure gradient between the tropics and the Arctic. And so one of the things that we think will happen is that as the Arctic gets warmer, that gradient of temperatures becomes weaker. And so the jet stream then becomes a bit more wobbly. Or the jet streams, if you will, become a bit more wobbly, and then does allow more cold air to come down and have more of those kinds of cold air outbreaks, which actually may be driving particularly some of the northern states why it would be possible to see why it would be projected to have more likely of having a fall spring in the future. So I think that's what you're referring to from what you're saying here, but feel free to let me know if I'm completely wrong in my interpretation, excuse me.
So do we have any other questions, comments? Okay, otherwise I guess we can let you guys leave sooner. I will send to you all a survey, and please let us know how we're doing with this new webinar series, and what other topics you would like to hear about climate change and climate adaptation strategies, especially in the state of Texas. Please, if you can attend the presentation tomorrow, we will have another great presentation regarding phenology and doing habitat restoration with native plants. Erin Postumus and Alisa Rose Martin are our presenters tomorrow. The webinar will be at 12 p.m. so Central Time. So I hope to see you guys tomorrow as well. And thank you so much for your comments. And we hope to see you soon again.
Thank you all. I appreciate it. Thank you for having me.